Hi everyone, I'm Aditya Kusupati, a PhD student at University of Washington. Today I'm going to present about LLC, Accurate Multipurpose Learned Low-Dimensional Binary Codes. This is joint work done with my colleagues at UW, along with my advisors Pratik, Sham, and Ali. Before we go into LLC, let's talk about the basics of multi-class classification. Multi-class classification tries to answer a multiple choice question among L options or classes. Typically, this is solved using L binary classifiers, where only one of the binary classifiers has the correct answer. So the total probability of all the output classes should sum up to 1. The pipeline often involves an image being fed to a featurizer, often a neural network, to get a d-dimensional real representation. On the top of the d-dimensional real representation, we learn L d-dimensional binary classifiers or hyperplanes in order to figure out if the dog belongs to a particular class. At the end, we get a one-hot vector out where dog is activated and every other class is 0. Let's talk about the costs and trade-offs involved in multi-class classification in a linear classification setting. Assuming constant featurization costs, linear classification often scales linearly in terms of dimensionality of the representation and the number of labels involved. So it's order of DL. So potential alternatives include tree-based data structures where your cost of compute reduces to order of log L, but your memory still scales as order of L. Uh, and the other alternative is embedding based methods where you take the d-dimensional representation, project it into a low dimensional space K, and then have a linear classifier on top of the K dimensional space. This changes the both compute and memory scaling to order KL, where K is much less than D, which often helps in your compute and memory efficiency gains. Before we go into learnable binary codes, let's talk about what output codes for classes even mean. Typically, each and every single class is represented by a one hot vector, which indirectly implies that every single class is equally independent and has no correlation whatsoever, which is not true. And coming from a computational perspective, it's very sparse. So, can we do better? The similar observations led to the creation of error correcting output codes, where every single class is encoded with a shorter binary code than its one hot counterpart. For example, ball can have two active bits, whereas car can have only one active bit, but they can be just represented by using 3 bits instead of the usual five in a five-way classification problem. So the problem we are trying to solve with output codes is we want to build a binary codebook for classes, and then further use this to learn instance codes as a multi-label problem. This reduces the cost of both training as well as inference to sublinear, that is order log L, if you are doing it right. Even though empirically and theoretically output codes make sense, they do have some shortcomings. The first one being the construction of the output codes themselves. We often require annotations like attributes or side information like hierarchy in order to build these output codes, and which are not cheap. And if you want to go for a cheaper option like random bit codes, you don't exploit the correlation across the classes and end up with larger bit codes than usual, while being as inaccurate. When we try to learn everything from scratch, it turns out all of these codes of every single class try to collapse into a single code, often trying to escape the problems of optimization, be it with alternating minimization or continuous relaxations. In the end, this results in inaccurate classification or retrieval performance, and often also relies on not so tight bit codes, which are much larger than order log L. So, for an ImageNet 1000 class classification, maybe you might be requiring, say, 100 bits, which is far from optimal, which is around 10 or 20. So, we ask the question, can we learn accurate and tight output codes without using any side information? I would not be considering class labels for every single instance as side information, but anything else apart from that would be considered side information. So the most key observation of the paper is, how do we represent classes, or like what actually means a class representation. One hot is of course a representation, but can we do better? And it turns out the classifiers we learn as part of multi-class classification are great at representing the classes themselves. So for an ImageNet classification problem using ResNet 50 classifier, you have a 2048 dimensional real vectors corresponding to every single one of the 1,000 classes. And what did we do? We just took each of them, took a pairwise inner product to show how correlated these learned representations of classes are. Um, in this heat map, you see regions lit up, which denotes higher correlation between the classes, which also corresponds to the underlying hierarchy of WordNet on which ImageNet was based on. So now that we have strong class representations which are accurate, we want to make them as efficient as possible. So how do we make these things low dimensional as well as binary? It turns out we can have a linear classifier on the low dimensional space of k dimensions, which is much, much less than d and often similar to order log L, by using the embedding based methods we talked earlier. All we need is a projection matrix P, which projects from d-dimensional real space into k-dimensional real space, followed by a classifier which takes it back to the L-dimensional space. However, because we want our class representations to be binary, I would be binarizing the linear classifier. And when I say binarization, I mean the weights of the classifier are set to either 0 or 1 or minus 1 or 1, depending on your implementation. At the end of the day, we have a classifier where it sort of is the collection of all the class codes. Each of the class code is k-dimensional long, and we call this the codebook. So here comes the LLC method. It's a two-phase method where we first learn the codebook, and following the codebook learning, we use the codebooks to learn instance codes more accurately, and we further use both class and instance codes for downstream applications. So, how do we learn the codebooks? We learn every single aspect of the pipeline end to end using stochastic gradient descent. That includes the featureizer, that is the deep neural network, the projection matrix P, and the binarized classifier B of C. The hardest part here is binarization of the classifier itself, and it turns out we can learn this using straight through estimator from the binary neural network literature, where in the forward pass, all the weights are considered to be binarized, whereas in the backward path, the underlying real values gets updated by gradient descent. And this works pretty reliably and stably, that we learn 20 bit codes for 1,000 classes of ImageNet every single time reliably. Now that we have the class codes, we want to learn instance codes. So what we do is we warm start with the deep neural network from the phase one, along with the projection matrix, and generate a k-dimensional instance representation in real space. Now we treat each and every single column of the B of C, the binarized classifier, as the target output label for every single corresponding class. So you have a k-dimensional multi-label problem, and you solve it as k-independent binary classification problems. So you start with the real representation and you pass it through a sigmoid in order to get probability estimates of every single binary code, every single hyperplane you are trying to estimate in the k-dimensional space. And you then try to regress it to the binary code of the corresponding class. Eventually, after some epochs of training, it saturates and it gets to a place where you can threshold it and get an instance code out. We call the binarized multi-label predictions as the instance codes, and we'll be using them for downstream applications. The question is, how good are 20-bit codes actually? So what we did is we made a side-by-side comparison of heat maps as I did with 2048 dimensional real numbers, and it turns out it's pretty much the same regions lighting up visually. You can look for more discussion on quantitative comparison of these things in the paper. Um, and another visualization is trying to discover a taxonomy using the 20-bit learned codebook. And using agglomerative clustering, we figure out that 20 bits are good enough to distill a lot of high-level semantic information. And they cluster things like marine life and amphibians together, while reptiles and domesticated animals are thrown far apart. And this is a discovered taxonomy for the first 50 classes of ImageNet 1000. So at the end of the day, we have a two-phase pipeline where at the end of the first phase, we end up with a code book, and following that, we use it to learn the instance codes. How do we use these instance codes and class codes to make things more efficient? That's where the decoding schemes come into picture. So the first and obvious decoding scheme is exact decoding, where the instance code has to exactly match the ground truth class code. So we take an instance code, make it an integer, do an inverse lookup from the code book, and we get the class label. And this turns out to be extremely efficient because it scales as order log L plus order 1 for hash lookup, which is much, much better than any real valued classifier out there. However, on the other extreme is minimum Hamming decoding, which tries to retrieve the closest class code for an instance code using minimum Hamming distance. This is very similar to inner product search, which most of the real value classifiers do. So we take an instance code, we do a matrix multiplication or a Hamming distance computation, and you get the class label by just taking the minimum Hamming distance out of the potential labels. Even though this is not as efficient as exact decoding, this is still much more efficient than its real valued counterpart because of the lack of real valued overhead, compute overhead, which is about an order of magnitude usually, along with the scaling depending on k, which is much, much smaller than the usual d. So we'll talk about three main applications. The first one is efficient multi-class classification. We, for the first time, do ImageNet 1000 classification with just 20 bits. And we also show the trade-offs between multiple decoding schemes. We also do efficient image retrieval with just 10 bits for ImageNet 100, where we try to retrieve the closest images for a given query image. And this has a high potential application for high recall retrieval in real-world search systems. Last application is slightly out of the box. It's out of distribution detection, where we try to do out of distribution detection for a given instance. If the instance's code doesn't belong to the class codebook, you can read more about the experimentation on OOD in the paper. Coming to the main result of image classification for ImageNet, we compare 20-bit bit codes using ResNet 50 backbone. An obvious baseline would be random codebook with 20 bits, which learns 1,000 unique codes, and its accuracy is about 67% with minimum Hamming distance accuracy. While the other two codebooks, CC and SPD, are the ones which are built assuming that they distill the hierarchical information from the pre-trained linear classifiers, and they suffer from codebook collapse, each of them learning around 800 and 950 class unique codes respectively. But SPD codebook improves upon the accuracy by about 2% over random codebook despite the code collapse, showing that the hierarchy matters to a great extent. However, LLC outperforms every one of these baselines by about 5% on minimum Hamming distance and about 3% on exact decoding, while learning 1,000 unique codes exactly, reliably every single time. So LLC learns more accurate, tight, reliable codebooks. And the surprising thing is ResNet 50 with the 2048 dimensional real representation under linear classifier gets to 77%. So we are only 2.5% lower in accuracy compared to ResNet 50 for minimum Hamming distance. But the 9% drop in ED is also not a big deal because of the computational gains it might be providing. We also do an ablation where the classification accuracy is searched along with the number of bits, and we figure out as the number of bits increases, as expected, minimum Hamming decoding increases the accuracy, but exact decoding increases initially and then decreases further, and it's potentially due to the uncertainty in estimating the number of bits as we increase the number of bits to be exactly decoded. This is an open question, and we're consistently working towards a solution. The second application is image retrieval for ImageNet 100. The image retrieval setup is encoding the image under database of images using instance binary codes. For a given query image, we want to retrieve the images of the same class, and we measure the performance using mean average precision at 1,000. And for a ResNet 50 backbone, it turns out LLC with just binary representation does as well as real valued 10-dimensional representation with this 10 bits, which is quite surprising and maybe leads us to rethink how we want to represent real numbers in general. We also compare LLC's retrieval performance with baselines, which are explicitly designed to learn only instance codes. And while LLC's instance codes come as a byproduct of its classification pipeline, it turns out LLC is much better than the state-of-the-art image retrieval performance baselines, which work on hashing and instance codes. Lastly, we worked on a bunch of ablations. We figure out we can do a bunch of tricks to make the codebook learning much faster. We also discuss about linear and Hamming separability as two different aspects of separation in high dimensional spaces. And we also talk about a very efficient transfer learning method, or like deployment method called nested codebook learning, which you can find in the paper. Um, the first and the last question I asked in the paper is, are these learned codebooks interpretable? And the answer turns out to be no. So what I'm showing right now is the hyperplane 4, where the left is the most positive bit 1 predictions, and the right are the most positive bit 0 predictions, and it turns out there is no correlation whatsoever. In summary, LLC is the first method to learn both class and instance codes. There's a lot of future work to be done. I'm happy to chat in the post session. Thank you.